Hey everyone, and welcome back. So before we can get to implementing merge sort, we're going to need to take a look at this fundamental computer science concept that our merge sort implementation is going to leverage. It's not exactly an algorithm per se, but rather a programming technique. This technique is called recursion. Recursion is a process where we break down a more complex problem into smaller instances of itself, solving the simplest instance directly, and using those solutions to construct solutions to the larger instance. In programming, this is accomplished by having a function that actually calls itself. This all sounds rather abstract, so allow me to demonstrate using this example of a task of adding up natural numbers in order like this. Let's say we have a function where we want to accomplish the following. We want to, given any natural number, such as 2 or 5, find the sum, like this, of all of the natural numbers leading up to that. So for instance, this would be the result of plugging in 5 to our function. Now before we get into this, know that recursion is just another way of thinking about a problem. Anything that can be solved recursively can also be solved iteratively. That is to say, without using recursion. But for some problems, recursion lends itself to a much more elegant and natural solution. And so before we write a recursive function here, let's actually solve this simple problem iteratively first, just to get our bearings, and have something to compare with once we write our recursive function. So first we're solving this in the more or less normal, typical way that we would solve a problem in programming. What we're going to have to do is we take our starting number and we perhaps have a while loop where we progressively decrement this number while adding the decremented number to a running sum. And then once we have hit 1, we know we're done. And so then we return. So it will probably look something like this. We will keep track of a sum variable that we will start off as our n parameter here. And then we'll iterate through a while loop where as long as our n value is greater than 0, we will go through and decrement our n and then add n to our sum. And then we will return the sum. Okay, so this is how we express this problem iteratively. And now let's take a look at how we might express this problem recursively. So I will create a new function definition here. So the structure of any recursive function usually takes this form. We have two fundamental cases that we need to deal with, a base case and a recursive case. A base case represents the most simple possible outcome of the problem. A base case represents the simplest instance of the problem with a known solution. So in the case of our natural numbers problem, the simplest possible version of this problem that we can think of is one where n equals 1. Because in this case, we actually don't need to do anything at all. We simply return 1. And so to start off, we will write this base case. So if n equals 1, we simply return n. And this is our base case. And then finally, we need to create our recursive case. The recursive case expresses the solution of a problem instance in terms of solutions to smaller instances of the problem. And this is where the recursion aspect, that is to say the function calling itself, comes in. So we will create another case here in this if-else branch, and this will be our recursive case. So I think it will be helpful here for me to just write this out, and I will retroactively explain what I have done. So we're going to, for our recursive case, say returning n plus a call to this very same function, where we put in as a parameter n minus 1. And so here we actually have the entirety of our recursive solution to the sum of natural numbers problem. So what is actually going on here in this recursive case? So the recursive case in a function is essentially the catalyst that propels this function into successive self-calls, which progressively break down this complex problem into a simpler, more manageable fragment. We can see that when we invoke this, we're actually plugging in whatever our current n is in whatever call of this function we're on, and subtracting 1 from it. We can think of this as sort of equivalent to what we were doing up here in our iterative solution where we decrement n. So what's going to happen is that we will eventually, if we keep decrementing n in this way, eventually one of these calls is going to hit not the recursive case, but it's going to hit the base case. And in this case, we can say that the recursion has more or less like reached bottom. Like we have all of these nested function calls that are waiting to return. And once we hit the base case, all of these function calls will start to propagate back up the chain, adding their results together until eventually, in our very first call, we will arrive at the correct answer. So don't worry if you're still a little bit perplexed at this stage. Recursion does take a little bit of time to get used to, as it's a totally new way of thinking about how to solve a problem. Before we move on to another recursion example in the next video, let me at least prove to you that these two functions are the same. So I will test both of these. So we're going to print the sum of natural numbers iterative 5 and print the sum of natural numbers recursive with 5. Let's see how that goes. And there we go. We can see that they give us the same answer. So these two functions, despite taking very different paths to get there, are solving the same problem. Except again, in the recursive case, we're just using these repeated calls to the function to break this problem into its constituent smaller parts. Hello again, and welcome back. We're continuing our section on recursion here with a slightly more complex but illustrative example. So the example we're going to be working with here is the Fibonacci sequence. So if you've never heard of the Fibonacci sequence, it's basically a sequence of numbers that is defined by any given element being the sum of the previous two elements. You can see here that 2 is the sum of 1 and 1, 3 is the sum of 1 and 2, 5 is the sum of 2 and 3, 8 is the sum of 3 and 5, etc. The Fibonacci sequence is kind of a classic example of recursion because even mathematically, its definition is necessarily recursive. So before we write any Python here, we're going to actually step through the mathematical definition of the Fibonacci sequence as if it were a recursive program. And this will hopefully illustrate not only how the Fibonacci sequence works, but also how recursion in general works. So before we step through an example solution, let's first get our bearings by writing out the formal definition of the Fibonacci sequence. So we start out with our two base cases, and this is the case even in the mathematical definition as well. So the Fibonacci sequence, I'll be notating it with function notation here. So f of 0 is defined as being equal to 0. F of 1 is defined as being equal to 1. For any n greater than 1, the definition is as follows. F of n is equal to f of n minus 1 plus f of n minus 2. So remember that in this definition, n represents basically the index of our Fibonacci sequence. It does not represent the actual value at any given point, but instead it represents the index. So we can see encoded here that for a given n, so let's say 3, the Fibonacci number is going to be equivalent to whatever the value of n minus 1 is. So in this case, n minus 1 would be this element right here, and whatever the value of n minus 2 is. So this value here, and so we can see that this becomes 3. So let's walk through every single recursive step here in more detail. So yeah, let's say we are solving this for an n equal to 3. So we want to find f of 3. So first, let's plug this into our Fibonacci sequence definition here and see what we get. So our n is greater than 1, so we're working with this definition right here. So we know that f of 3 is going to be equal to f of 3 minus 1, so f of 2, plus f of 3 minus 2, so f of 1. So we actually can see already that we have hit a base case. So f of 1 is always going to be equal to 1, so we know that this is going to be simply 1. But now we need to figure out what f of 2 is, because f of 2 is not yet a base case. So f of 2 is going to be equal to 2 minus 1, which is 1, plus f of 0. And so now we can see we have hit our true base case here, because both of these are already defined. So we know that this is going to be 1, not an exclamation point, this is going to be 1, and we know that this is going to be 0. So we can reduce this down to 1. So we can see now that this f of 2 up here is also equal to 1. So then we know that f of 3 equals 1 plus 1, or 2, which is the correct value here for the Fibonacci sequence. So we can see here how recursion is used. Notice that when we stepped into this f of 2 here, we kind of repeated the whole process again. And if we started at a much higher number, we would simply keep repeating this over and over with this recursive definition until we hit our base cases. And so it turns out that this is going to be exactly how we're going to write this function in Python. And so using this mathematical definition of the Fibonacci sequence and recursion, let's see if we can replicate this in code. So I'm going to define a function that I will call Fibonacci. And first, let's write our base cases. So we know that if n is less than or equal to 0, we're going to return 0. Also, we know that if n is 1, that we're going to return 1. These are the base cases that are noted in the mathematical definition as well. And finally, we'll write our recursive case. So all we have to do here is express this definition of the Fibonacci sequence in Python, which it turns out is almost identical. We call recursively the function that we're in. So Fibonacci at any given n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. And this is actually it. We have successfully encoded the definition of the Fibonacci sequence into a recursive Python function here. So just to make sure this works, let's try it out. So let's try it on 3. Okay, here we go. So it gave us 2, that's correct. Let's try another one. Say 8. Okay, 21. And so checking our sequence up here, see that 1, 2, or no, we don't start at 0. So 1, 2, 3, 4, 5, 6, 7, 8. There we go. We got the right answer. So this is an example of a function that really lends itself well to being expressed recursively. Not even though pretty much every problem can be expressed recursively, it's not always a good idea to do so. But for some, like this, it can naturally make more sense to do it this way rather than iteratively. So before we move on to deploying our recursion knowledge in implementing a more complex sorting algorithm, merge sort, we're going to try a challenge that we'll answer in the subsequent video to just test your knowledge of recursion so far. So the challenge will be to use recursion to calculate the factorial of a given number. So the factorial is defined as similar to our sum of natural numbers up here. Factorial is defined as all of the numbers in the previous sequence, but kind of multiplied together. So the factorial of 3, which is written like this, is equal to 1 times 2 times 3. and so on. So see how you do with this, and we will answer it in the next video.